Hello, my name is Alex and I'm a PhD student at NYU and I'll be giving an overview of PooDLe. Pooled and dense self-supervised learning from naturalistic videos. This work was done in collaboration with Chris Huang, Yuan Xiong, Yan LeCun, and Meng Ren. The goal of this work is to understand the implicit biases built into self-supervised learning via the curated data that it depends on and how to overcome these limitations and effectively learn representations from widely available naturalistic videos. Self-supervised learning has demonstrated incredible results on many vision tasks, but these methods depend on ImageNet or ImageNet-like iconic datasets, such as this image of a dog where there is a single clear subject that is cropped to fill the majority of the frame. This is in fact its own form of supervision, and furthermore, balancing these so-called classes within the data may constitute supervision as well. However, in reality, the visual world doesn't usually present itself this way. Instead, it appears more like this frame from PooDLe, a self-driving video dataset. There's no clear single subject, and there are many independently occurring objects of varying sizes. In our work, we investigate the challenges when learning from this type of video data and propose a method that overcomes them. First, taking this dense scene, we can identify two random crops, but they produce no semantic correspondence. This makes it difficult for conventional pooled SSL methods to learn transformation invariant representations. And furthermore, as objects are of variable size, we encounter a size imbalance problem. Here, we see a long tail of the fraction of pixels occupied by each class in PooDLe 100K. And in particular, small but important classes like humans, traffic lights, and traffic signs are difficult to learn from in this data setting. Introducing our method, we sample two global crops from frames that are delta t seconds apart and compute the optical flow using raft between them. We also sample subcrops from each global prop, shown as the beige squares on each frame. The local and global crops are passed into the same encoder before they are used to compute our dual objectives. The global crops are applied for the dense objective, while each smaller subcrop pair is used to compute the pooled objective. We also introduce a spatial decoder module between our dense and pooled objectives with a small amount of trainable weights to efficiently upsample our feature map for dense self-supervised learning. It also has a lateral connection to the encoder to help propagate information about smaller objects through to this dense objective. We train and evaluate PooDLe as well as other SSL methods on PooDLe 100K. We find that PooDLe outperforms existing models using linear readout as well as a heavier uppernet readout head. We also outperform the ImageNet baseline, which was trained on balanced iconic data. And furthermore, we find that PooDLe is composable with the pre-trained semantic representation from ImageNet pre-training and further improves on its results. We also set up an experiment separating PooDLe 100K classes and subcategorize them into small and large, rare, and common groups. We find that the ImageNet trained models perform well on small objects due to the iconic size normalization and the rare objects due to class balancing, whereas the dense methods like FlowE perform much better on the large classes that occupy more space in the training data. Differently, PooDLe outperforms other PooDLe trained models across the board, but particularly on small objects, thanks to our spatial decoder module. And we see that applying PooDLe training on top of pre-trained semantic representations does not override the existing benefits of learning from iconic class-balanced data. We also extend these observed differences visually into semantic segmentation results. Given these images and the ground truth label, we can see that the supervised iconic models perform well on MIOU but have noisy, splotchy solutions, while dense methods have more clean-looking solutions, but they miss smaller classes, which greatly affects the class-averaged MIOU metric. Finally, we find that PooDLe improves the recall on these small object classes while also maintaining smoother, cleaner segmentation maps. For more experiments where we train on walking tours, our new benchmark walking tour semantic, ablation studies, and more information on our subcropping strategy, please see our paper.